Hi, Stephen here. Now, I have this government job, and lately some of my workmates have asked me to explain blackbody radiation. Okay, so what is blackbody radiation? All surfaces above 0 Kelvin radiate electromagnetic waves. Blackbody radiation is the radiation that comes from a special type of idealized surface called a black body. This phenomenon is really just a conversion between two types of heat. Heat is the random kinetic energy between atoms and molecules of a block of material, but on the other hand, heat can also mean the low-frequency electromagnetic radiation that comes from your ray heater, or your microwave, or a warm campfire. We use the same word to describe two phenomena because they are interchangeable. When heat rays strike a surface, the electromagnetic energy hits the charged electrons and nuclei and gives them kinetic energy, so they vibrate. Each substance has its own set of resonant frequencies which it can absorb in this way, and more complex substances tend to have more modes of vibration and therefore absorb more frequencies. And we characterize a color by the frequencies that the surface doesn't absorb, but either transmits or reflects. A black body is a hypothetical surface that converts 100% of all frequencies into kinetic energy. That means when you shine light onto it, it all turns into heat. Nothing passes through, nothing reflects back. Most things in nature work both ways. When you heat an object, the charged particles bump into each other. Electrons get pushed into higher electron shells, and so some of that heat energy gets converted into electromagnetic radiation. The released frequencies are the resonant frequencies, the very same frequencies that are absorbed in the first place. So when we talk about black body radiation, we mean the radiation that comes from a hypothetical object whose molecules vibrate at every conceivable wavelength. It emits radiation at every wavelength by virtue of its random kinetic energy. It emits electromagnetic radiation, and as it goes colder, it loses energy unless it is connected to some heat reservoir. Alternatively, you could put it inside a reflecting box, and the kinetic and electromagnetic energy would equilibrate. This video is about the spectral distribution of black body radiation. How much energy does a black body radiate at each frequency or wavelength? And that's the Planck distribution law, either in angular frequency or through a change of variables in terms of lambda, the wavelength. Normally in physics we use natural units where the fundamental universal constants, the speed of light, the Planck's reduced constant, and the Boltzmann constant are all equal to 1. But for this special case, we'll leave these constants in so that you can see exactly what's going on. It's a trivial step from the Planck distribution to the Stefan-Boltzmann law. You just have to integrate over the spectrum to find the total power coming from a black body. This integral, the Bose-Einstein integral, evaluates to pi to the 4th over 15. These factors comprise the Stefan-Boltzmann constant. Alternatively, if you differentiate the Planck distribution, set it equal to 0, you find the peak frequency or wavelength. Wien's displacement law says that the peak wavelength is inversely related to temperature. So how do we prove Planck's law? I'm going to introduce some basic thermal physics, starting with the canonical ensemble. Now, the simple harmonic oscillator is the quintessential physical system. Say you have a classical particle, mass m, in a one-dimensional potential well. So this is the total Hamiltonian. When the system begins at a definite start point, the Hamiltonian equations of motion say the time derivative of our position coordinate is dh dp, whereas p dot, the time derivative of our conjugate momentum, is negative dh dq. You end up tracing out a level path in phase space. It's an ellipse. In statistical mechanics, we deal with uncertainty. Instead of a particular point in phase space, we have some probability distribution of likely places it can be at any given time. If we are completely ignorant about the system, then it can literally sit at any point in phase space with equal probability at any time. Additional information, like the energy content, can restrict us to an accessible subset of system phase space. For example, if we know the energy content but nothing else, the system can occupy any point on this ring with equal likelihood. Alternatively, instead of restricting ourselves to a particular ring, we can place a system, the simple harmonic oscillator, inside a temperature bath, or energy bath, or heat bath. An energy bath, or temperature bath, heat bath, is essentially a larger system, the environment, that can exchange energy with our system, and it prefers a higher energy state. Specifically, the phase space volume dedicated to a particular energy level E is an exponential function of E. Beta here is defined as 1 on kT, where T is the absolute temperature and K is the Boltzmann constant. The system and environment together make up our universe, and the universe weights all points equally. This means low energy states for the system become exponentially more probable because they imply more energy in the environment, whereas the higher energy states imply less energy in the environment. In fact, if sigma of E, the density of state, is the system phase space volume dedicated to energy E, then the universe dedicates this much phase space volume to it. Sigma times the environmental phase space volume, which is an exponential factor of total energy minus system energy. And if I wanted to calculate the average energy in the system, I would take a weighted average over all the accessible states. The probability to achieve energy E at any given random instant is proportional to this, but probabilities add to 1, so we normalize by dividing by this integral, which is a function of energy bath temperature, 1 on K beta. And that's called the canonical partition function, Z, and it's essentially the Laplace transform of the density of state. Okay, so what is the average energy? If this Boltzmann factor exponentially favors low energy states, okay, at first the numerator and denominator both look like daunting double integrals over the x and p coordinates of phase space. But notice how the denominator is just two sequential Gaussian integrals? And what if we break the numerator into two pieces and multiply by beta inside the integral and divide by beta outside it? In my other video I explained why the Gaussian integral evaluates to root pi. If you have x squared e to the negative x squared, you can integrate by parts and show that it reduces to the Gaussian integral. The boundary term vanishes by the rule of L'Hopital. If you apply this to the numerator of our first problem, you see that the whole expression collapses down to 1 on beta. In other words, the mass and spring constant have absolutely no bearing on the energy content in the classical harmonic oscillator in a heat or temperature bath. Every simple harmonic oscillator in the same heat bath has the same energy. The same energy is directly proportional to the temperature. That's called the equipartition theorem. Now, why is this a problem? Well, let's say you pluck an ideal guitar string. How many modes can it vibrate? It has the first mode of vibration with frequency c on 2L, where c is the speed of propagation of the standing wave, and you also have an infinite number of other frequencies. Each harmonic is a simple harmonic oscillator. They all work independently. That means if you hit a guitar string with random energy and let the string sit around long enough, all of these modes will equilibrate and hold the same amount of energy. But since there are infinite modes of vibration, the ideal string would, in classical theory, hold an infinite amount of energy at a given temperature. It's like the magical bag of Mary Poppins. Now that's a little unsettling that classical mechanics would predict this for an ideal string. The real guitar string is actually an array of damped simple harmonic oscillators where the higher frequency modes decay faster. Okay, but this defense doesn't work for a microscopic system where there is no friction, like a gas. The gas molecules, if you have a sample of gas, store energy through their translational and rotational kinetic energy and every mode of vibration within each molecule. That includes every chemical bond, every electron, and all of the interactions between the quarks that make up protons and neutrons. Any simple harmonic oscillator, no matter how small, would be reflected in the heat capacity of a gas. And unfortunately, this doesn't agree with the experimental findings. It was one of the earliest clues that alerted physicists in the world that something wasn't quite right. So how do we reconcile theory with reality? Quantum mechanics. QM is a complete video series in itself, but let's just see what happens when you shrink a simple harmonic oscillator to scales where quantum mechanics becomes relevant. We have here the time-dependent Schrödinger equation, whose wave function, psi of t, is a complex exponential times some eigenstate of the Hamiltonian operator. The Hamiltonian operator acting on little psi equals E times little psi, by definition. Okay, and you can see that this solution works if you substitute back to the original Schrödinger equation. So, what are these position eigenstates? We're looking for functions psi of x such that E psi equals this thing. Let's multiply both sides by 2 on h bar omega, where omega is just shorthand for root k on m, and put it all to one side. We'll pick a length scale that makes this factor in front of the second derivative term vanish, and rename the function as u, so that u of big X is actually just psi of little x. Let's rescale our eigenvalue e so that we have lambda equals 2 on h bar omega times e. So this is our second order differential equation. What solutions exist? You can specify any eigenvalue, lambda, and solve this equation, but it won't necessarily produce a normalizable wave function. The solutions that matter are such that the norm of psi, the absolute value of it, integrated over all positions, comes to some finite number. We divide this factor out and interpret the normalized wave function as the probability density cloud, or the square of it is the probability density cloud of the particle on a simple harmonic oscillator. Now, x in this integral ranges from negative to positive infinity. The only way this integral can converge is if psi tends to 0 as x gets infinitely large. This only happens if lambda is some odd integer. Why? Well, we'll actually work out the power series solution. First, a little trick. If we switch from u to v, we have a second order differential equation for v of x. Let's find the power series representation for v. So v is anx to the n summed over n, and we see the first and second derivative here. All we have to do is sub in and solve for an. The first term vanishes for n equals 0 and n equals 1, so let's just relabel the index by substituting n in the place of n minus 2. So if the left and right hand side have to match for all x, it follows that x and x squared and x cubed, all those coefficients add to 0. And that is how you get the recursion formula for the coefficients in this power series solution. So a0 and a1 are arbitrary integration constants, but all subsequent power series terms are dependent on the ones before it. If lambda is an odd number, the series will converge, and the solution will be e to the negative x squared on 2 times some finite polynomial. And every term in this finite series will integrate from negative to positive infinity to give some finite number. You can check this by integration by parts to produce this reduction formula. And for odd powers it also works. Okay, but if lambda is not an odd integer, then you have an infinite series, and so the stationary state wave function equals this thing times e to the negative x squared on 2. Now, having e to the x squared on 2 in the denominator is a very strong inhibitory control. You might wonder if it's enough to make this wave function tend to 0. If it did, then there might be some hope of the integral of psi squared converging, but alas no. This will be bigger than 1 for all x beyond a certain value, and to see this, multiply this across and compare the power series expansions. If the x to the 2n coefficient is 1 on n factorial 2 to the n, then we have this recursive relation. Now compare it against our recursive relation for the even terms on the left. Sorry? Okay, so this inequation guarantees that all coefficients on the left will be greater than the right. This means that the even terms are not normalizable, and we have the same argument for the odd terms in the power series, except with an extra factor of x. Higher order terms dominate in any power series, and therefore all x beyond some limit will make psi greater than 1, and the integral of the square of the wave function therefore has to diverge. Well, that settles it. Lambda has to equal some odd number so that this power series solution terminates as a finite polynomials. These are called Hermite polynomials. We defined lambda as 2 on h bar omega times our original eigenvalue, energy. This means the valid energy eigenstates are h bar omega times n plus a half. That's the one thing that everybody seems to remember about the simple harmonic oscillator, and it means that the average energy in thermal equilibrium is not an integral but rather a weighted sum with probability e to the negative beta times energy divided by the sum of all these Boltzmann factors. This sum on the bottom is the partition function, and we can see the numerator is the derivative of the partition function. So we can conveniently evaluate this sum if we differentiate the partition function. The partition function is just an infinite geometric series. So there we go. Z dash on Z is just the derivative of ln Z, which is this quantity, so we can differentiate, and there you have it. The average energy in a simple harmonic oscillator at temperature 1 on K beta. The first term here reflects 0-point energy, the minimum that all harmonic oscillators must hold because the Heisenberg uncertainty principle forbids us from simultaneously knowing the particle is at zero velocity and sitting at the lowest potential energy. In the classical limit, where h bar tends to 0-point energy vanishes, and this other term, by L'Hopital, tends to omega on beta omega, which is just 1 on beta, our classical answer. But notice how if h bar is not 0, then our answer does in fact depend on omega, which is our shorthand for root of k on m. In other words, harmonic oscillators store less energy than classically predicted. The stiffer it is in relation to temperature, the less it stores. What does the quantum harmonic oscillator have to do with black body radiation? A black body, you recall, is a surface that resonates at every electromagnetic frequency. Consider for a moment an L by L by L reflecting cube. Its electromagnetic modes of vibration must fit into the box vertically, horizontally, and laterally. This is like a three-dimensional guitar string with displacement sine pi mx x on L times sine pi my y on L times sine pi mz z on L, where m, x, y, and z is some integer triplet. The natural resonant frequency of a given mode is just the magnitude of m that you see here times pi c on L. Let's say this box exchanges energy with the vibrating molecules in its walls so that all modes eventually equilibrate. Classically, the ultraviolet catastrophe rears its ugly head, and at any temperature above absolute zero, the infinite modes of vibration would suck up an infinite amount of total energy. But in the quantum mechanical paradigm, each mode holds some 0-point energy plus some quantity that vanishes for very high values of omega. And if we measure energy relative to the 0-point energy, then we have a sum that potentially converges. That's exactly what we find. Okay, so how much energy is in our box over and above 0-point energy? Let's add up all these modes of vibration. The factor of 2 comes from the two polarizations of light that exist for each mode, and this finite box is our approximation to a black body, but in the limit, all frequencies would be represented. Instead of this discrete spectrum for integer values of mx, my, and mz. This implies the box grows infinitely large and the sum becomes a continuous integral. We can substitute omega x, y, and z to mean mx, y, and z times pi c on L. And this gives us our factor at the front when we change variables. This factor of 1/8 here comes from changing our limits of integration to the entirety of three-dimensional space instead of just one octant, the positive x, positive y, positive z octant. Now if we do this, we can change the spherical coordinates where by radial symmetry the zenith and azimuth integrate out to give a factor of 4 pi, and we only integrate over the magnitude of omega. And there you have it. This integral evaluates to the total energy stored in our infinitely large box, over and above 0 point energy. And not surprisingly, it is proportional to the volume of the box. So dividing by Z gives us the energy density. The integrand here is the energy density in the box per unit of angular frequency. Every point inside the box radiates some energy to its neighboring points, and in equilibrium each point is gaining just as much as it's losing. So what if the box has a hole? How quickly does energy leak out? Well, some dots here travel perpendicular to the wall, while these guys travel on an angle. This epsilon is spread evenly over 4 pi steradians, so the spectral energy density is epsilon times d omega over 4 pi, and each beam of cross-section A cos theta travels at the speed of light. So the spectral power in this beam per steradian, called the spectral intensity, for a hole with this area is A cos theta times epsilon d omega on 4 pi times the speed of light. If we have a black body with the same modes of vibration as our infinitely large black box, it will have the same spectral energy density within its volume and therefore emit electromagnetic radiation from every point on its surface at the same rate as a hole in the box. In other words, this number divided by area is the spectral intensity per area, the spectral luminance of a black body. That is, joules of energy per second, per square meter of surface, per steradian of solid angle, per hertz along the electromagnetic spectrum. Theta equals 0 gives you the luminance normal to the surface, and this is Planck's law. Now, if you integrate spectral luminance over the 2 pi steradians pointing outwards, you get the spectral illuminance, the energy leaving the body per unit of area per unit time. Okay, so integrating over solid angle is really just multiplying by sine theta, integrating over theta and phi in spherical coordinates, the zenith and azimuth angles. And you pick up a factor of pi when you do this. Now, if you ever want to scratch the word spectral from anything, you just need to integrate over omega. For example, let's integrate the spectral illuminance. Let's change variables so that u is beta h bar omega. This leaves us with the Bose-Einstein integral. We can show using complex analysis that it evaluates to pi to the 4th over 15, and beta is defined as 1 on kT. And so there you have it, the Stefan-Boltzmann law. And that, boys and girls, is black body radiation in a nutshell.